start. I guess everybody who wanted to come came. And um, um, we are going to talk about, first of all, you need to set up, not set up, I will be giving you assignments, not assignments, problems to try, and then I hope this will be an interactive process for the next 2 hours. So to be able to solve what I will ask you to solve, please access Google Colab or any other Python environment. Let me ask you, how many of you are familiar with the Jupyter notebooks?
Everyone.
Okay, everyone is familiar. Great. So and where did you use them?
We have a course in the first term. So we can manipulate the data, at least.
Okay, perfect. Great. So make sure launch some environment, either Google Colab or Jupyter Notebook on your laptop, or Google Colab on your laptop. So launch, and we are going to go through different exercises, and I will be asking you questions and waiting for your answers. We need to do a bit of econometrics and asymptotic theory here to start. We will start with very simple things that would then hopefully will lead to understanding of more complicated things. So why we need to talk about statistics and like asymptotics in a machine learning class? Well, one big reason for this is that ultimately, when you're trying to build a forecasting model, there should be a way for you to select the best model, or among among varieties of models, choose which one you trust most. And then also you might want to think about how much you trust a particular model or particular forecast. Like, what is your error band? This is a standard thing. You don't just, in many cases, you don't just come up with a single number for your forecast. You want to have you come up with some distribution of your forecast, like with the 5% probability, you would have that range of numbers. So that's one thing. And another thing, as I said, that when we're choosing the model, we need to have some sense of how we trust this model, how much we trust this model, and then that immediately leads us to the questions of like statistics, distributions, and things like that. So let me start with a simple example. I'm going to share my screen. Sorry, 1 second. Okay, everybody sees my screen, right? So I'm on Google Colabs. I just load some packages and let me see where I want to start. First thing I want to do is
Excuse
I
me.
want to, yes,
Would you send us this file?
not for now. I will ask you
Okay.
to just repeat what I'm doing. Well, let me see. Okay, I can actually send this file. Yeah, actually, yeah, I will remove everything that I have here and I can share it with you. Okay, let me drop it into the chat. Okay, that's the file. So let's see. I will start with a very simple random model that I come up with. Let's see. Sorry, a bit. Okay, suppose I want to work as a model like yt is equal to beta plus epsilon t. So I'm going to generate some random model like that where, let's say it's not beta, that's rho, where rho is a constant and epsilon is the error. Suppose I generate normal error with mean 0, variance 1, size t. So then, like suppose I said, rho is equal to 0 to begin with. Then initialize. And the next thing that I want to do, I want to run a linear regression. Say, yeah, I'm copy pasting here, but let's suppose I'm writing it from the very beginning. So I am initializing a model from a linear regression. I'm using a linear model package here. It's one of the packages in Python where you can load a linear regression. You can estimate a linear regression. So I initialize a model here. I want to feed the intercept, and that's all what I want to do. And then say I don't have any data. And everything I do is just running this regression on it. Would it work like this? I'm not sure. Let's see. No, it doesn't work. Let me initialize it with some just dumb value 60. No. Okay, perfect. So I just running a regression of YT on an intercept. And I'm interested in checking what is the value of the intercept. I randomly generate 100 values of the error, then generate YTs, which are 0 plus the error, and I want to estimate this row from this random sample. And I'm interested in regression coefficient 0. Let's see. Is this the one? No, this is not the one. How do you get it from the regression? Give me a second. Perfect. Okay, so I'm getting this intercept, and let's see, we can even do the plot and see how YT looks. No, not like this. Let's see. Well, I can always do this. Maybe like this. So this is my generated YT. I used some random sample. I used 0 row, and the coefficient that I got is 0.2. So how do I know that this is 0, not 0? Is 0.2, is it 0 or not 0? And that's a question for you.
We need some kind of p-value.
Perfect. We need to, great. We need to have some p-value or something, right? We need to do a test. Okay, and then I just want to demonstrate you that we can be doing it multiple times. And we can be getting negative values, positive values. We can be all over the place. Okay, perfect. And it's never exactly 0. And so we need to figure out, well, here it's as close to 0 as it gets. So we need to have some p-value. Or more generally, we need to do the hypothesis test. Now, in order to the hypothesis test, to test if this is truly zero or not, we need to think about, make assumptions about the model. So we need to understand, we need to assume something. Because there is no way to move forward here except for by assuming something about the model that like the error term and this coefficient. So we need to assume that this is the model. And then we can test if this coefficient is zero. Now, all of you have done it in econometrics analytically, and you know the analytic expression for rho. Here, what I want to do, I want to show you how to generate this like numerically, that test, because the test for the rho if zero or not. And then why I want to do it numerically, because I think it's illuminating first. Secondly, that would help you to get to harder cases once we start talking about time series dependence. Algebra there very quickly gets very difficult, but you can run numerical experiments, and these numerical experiments can help you to understand what's going on. Okay, so let me show how I'm going to do it numerically. What I'm going to do now, I'm going to generate my true model, my true assumed model, many, many times. In particular, I'm going to generate it, say, b equal to 10,000 times, and I will plot the distribution of the estimated coefficients rho. So I will be running it 10,000 times. And I will be doing this. So now I will be collecting all the estimated coefficients in this array. So I will launch it. So what I'm doing here, I hope it's clear. I'm just simulating it 10,000 times, drawing random errors and estimating the same specification to see numerically. I'm not interested in seeing it algebraically or analytically. I want to see numerically what, if my model is true, what would be the distribution of the estimated rho heads numerically. And one more reason why I want to do it, besides that it then will help you to understand more difficult cases when the algebra is super difficult, it also, this kind of exercise, this is the kind of exercise that you do with Bootstrap, so, or with cross-validation. And so doing these exercises with the simulated data will help you to maybe better understand what's going on when we go to resampling methods later. So anyway, I got my rho heads, and now I want to plot them. So in order to plot them, I'm going to use this hist plot, nice hist plot function from Seaborn library. That would give me very nice histograms. So I'm going to be drawing raw heads. I want to do the density. I want to show me also the fitted smooth kernel estimation of the density. I will show how it looks later. So let's do 50 bins. Let's do some custom colors to be nice. Let's do it. Alpha is the transparency. You can play around with these parameters. This is all for nicety, and then a bit more niceties. This is for the age of the boxes that are coming. You will see again in a second. You have never done it, and let's label it. And here called density. Okay, let's have it. Okay, this is what we get. Very nice. Very smooth, very nice. What we see here is that in theory, if our estimation is true, if our specification is true, then this is what we would observe. This would be the distribution of the estimated coefficients, which means that a new sample arrives of size t, which is 100 here. We estimate a coefficient, and it can be anywhere between like minus 0.4, plus 0.4, and it can be anywhere here. Which is interesting, right? Because we are really estimating the regression. We really know that the true model is the model with rho 0, but what comes out of estimate, rho can be all over the place. We can repeat this exercise with, say, sample of size, a smaller size of the sample, and see how it looks. Remember, before that, it was between minus 0.4 plus 0.4. Now what you see here, it's minus 1 plus 1, so it gets larger. The variance with a smaller sample, the variance of the coefficient gets larger. Now, of course, the other way is also true. If we do a sample of size 1000, we will get a much smaller variance. Observe. So the variance is smaller, minus 0.1 plus 0.1, but observe this blue line. This is what I made this kernel density estimate, KDE. If I do false, then it doesn't show me the kernel density estimate. If I make it true, then it shows me the kernel density estimate. And observe that that's supposedly the true smooth distribution of that coefficient. And this is not exactly normal. And it's interesting, actually, to lay it over with the normal distribution. Let's do it. So let's just out of curiosity, let's see how the normal distribution would look like that has the same mean and the same variance. So for this, I'm using this library from Python, SciPython stats, which is lots of SciPy is the thing, the library to go for many things. I'm of course, didn't say that I'm using NumPy everywhere, because NumPy, probably if you worked with the data and with Jupyter notebooks, you should be familiar with NumPy, because this is like the first thing that you learn. It's very good for manipulating with arrays, matrices, and things like that. The pandas are built over NumPy, and pandas is the thing to manipulate with the real data. Anyway, and then what I've used so far is the sklearn linear model, and then SciPy stats. Okay, so, and I'm going to layer over my histogram with the normal distribution. So let's see. One second. Well, let's go run the rest of it. NumPy mean raw flats, NumPy mean, oops, sorry, raw flats. So I'm going to take say 200 grid points between row mean and row max. That would be my row grid. And I'm going to calculate the density of the normal distribution, probability density function, over this grid with the mean row mean and, sorry, no, row mean, and with the density, standard deviation row estimate. Okay, once I calculate this, I can make a plot. Row grid, and let's make it okay, so this dashed red line is the normal density that I overlaid, and we see that this blue line is approximately the normal density. Okay, fine, good. So, and why it was interesting to lay it over, because, well, you know from the econometrics class that this is most likely is not, you know that it's normal, and then you know that also from seeing the graph, that is the histogram, you see that it looks like normal. So it's interesting to see if it's close to normal, and indeed we see that it's kind of close to normal, although not exactly. And perhaps we expect that as t becomes even larger, then it becomes even closer to the normal distribution. While it's running, I want to, so where do we go from here? As we said, we want to do the hypothesis testing. So then we see that this is normal, but then how do we decide if this number is really zero or not? Suppose we get an estimate like minus 0.05. Is it zero or not? So here we need to rely on the theory. We know that, let me write some text here. We know that, so the text will be appearing here as I'm writing. We know that if let's see. So if this is my specification, it's look here, then and errors are normal, ID, independently identically distributed normal with sigma squared variance. So by the way, this is done. I just want to look how it looks, check how it looks. Yeah, it's still, you see that it still doesn't look exactly normal, which is curious, which tells you that the rate of convergence might be relatively small, relatively slow, sorry. We know that it should be normal in the limit. Or maybe we should take more B's to construct it more precisely. So we can increase B 10 times. Let's see if it gets because this is still a numerical. We don't know, it's a numerical error or this is slow convergence. So we can get more B's, so increase the sample size for the row and see if it gets a better, closer to normal, but with smaller t. Because otherwise it takes too long to calculate it. Okay, back to this stuff. And here we know that so we know that this is what's going to happen. Let's then do this. Let's multiply our estimates of row head on square of t, which is, in this example, it would be 1000, and plot the distribution of this guy. And our assumption about row 0 is that it's 0. So we want to test if it's 0. And then for the error, let's suppose that we know the model. We are not estimating this parameter. So we know that it's 1. So literally, we want to check if this is equal to, we want to see how, sorry, we know from the theory that this should be close to a normal 0, 1 distribution if our error is normal 0, 1. Let's see if this is really the case. So it's done. Oh, very nice. So very still not normal. I don't know. Is it a numerical error or it's low convergence? I don't know. But let's continue. Let's do repeat this graph, but let's say rho 0 is equal to 0. And then let's do x equal to s square, sorry, np squared 2 multiplied by rho x minus rho 0. And now do x here. So do everywhere x. Oops. This means that's okay. And let me another thing. I want to bring it up. I also want to see how it looks, the values, if they're anywhere close to 1 and 0 and 1. So this is close to 0, but this is not really 1. This is 2. So am I missing something? Why the variance is 2? Sorry, not multiplied by 2. Square. Okay, close to 1. Okay, perfect. So it looks like this is true, and then I can use this information to test the hypothesis. And how do I test the hypothesis that the coefficient is close or not close to 0? I calculate p-values. Okay, let's do the calculation of p-values. And I just want to emphasize that it might seem like a bit dull what I'm doing right now, but I'm going to be repeating that exercise and changing the models. And at some point, I hope that you will be surprised with the results that you will see once I get to the time series. Okay, anyway, so let me move on to the calculation of p-values to test the hypothesis. So how do we do the p-values estimation? Let me see. Of course, I practiced everything many times before showing you this. So I'm, of course, using my prepared. Let's see, not this one. Stupid Zoom. Okay, this one. So what this here I calculated the numerical theoretical distribution of the calculated the distribution of the coefficients of that regression. Now suppose I repeat this exercise and now I do some new sample arrives. Let me copy paste from here. Also size t, I calculate all this stuff. And my raw hat is intercept. So I want to check if raw hat is far enough from zero. For that, I normalize it. Say I do the, let's call it t value. Oh, sorry. Select this t value raw hat. Better. And now let's first see what kind of t values we will be getting. Positive, positive, negative, negative. Okay, so sometimes it gets here, sometimes it gets here. How do we calculate a p-value of, say, this number? So by the definition, p-value is the probability to observe an event that is more rare than what we observe. This is just the intuition. Again, p-value is the, let me write it down, because I want to do everything from the first principles. P-value, so in noise distribution is the probability to observe an event that is more rare than what we observe. Okay, so in our case, what it means, we observe this value. What would be a more rare event? A more rare event would be under the null hypothesis of the true value 0. The more rare event would be something larger than this on the positive side, or smaller than, or like much smaller. So for our case, let me start writing how I can if t-val bigger than 0. Value is equal. I take x here. Oops, sorry. X divided by b. Let me write this. One sine x t-val divided by, let's say, sorry. Let's see. So what we see here, sorry, is that with such value t-val, in the true distribution, if the model is correct, the probability to observe something larger than this t-val is equal to 34%. Okay, let me pause here for a second and ask if you're following and you're understanding what I'm doing. Maybe I'm too rushing to, or maybe it's obvious what I'm doing here. Anyone?
Yeah, I've got a question. It's kind of obvious, but there is one thing that I don't understand. Is that you divide NP sum by B? Why do you divide it by B? Exactly.
Just to
by
calculate the percentage, because I didn't translate X into the, basically, I wanted, because look, if I do this, that gives me 0, 1, true, false.
Oh, yeah.
When I sum them.
Yeah, I got it.
Okay, so.
Okay.
Now, in order to calculate the p-value, again, as I wrote here, this is the p-value where I wrote it here, p-value of a continuous. Let me move it up here. P-value of a continuous distribution is the probability to observe an event that is more rare or than what we observe. So on the plus side, the more rare event with this probability, we observe a more rare event than this t-value. Then, of course, there is another value or with the equal that can be equally rare, but on the minus side. So let's do the minus. What would be the critical value or the corresponding value on the minus side? So let's call it t-val q. One tile x is equal to 1. Sorry, I need to, I'm always not to be, okay, because I calculate here larger, then I need to do the 1 minus this. Oh no, this is correct. And if I do lower, then I need to calculate 1 minus this. Because, yeah, I need to go to the larger side, right? So if t-val is positive, then I calculated all values larger than t-val. Then I, on the negative side, that would be the probability. Okay, and if it's negative, it's like this. Perfect. So let me write it a bit more under the our hypothesis 0. So let me start like this. Okay, that's about this. Sorry. So, and let me write the print all t values larger than equally rare. And okay, let's see what I've got. So, like for example, I'm getting 0.133, then the probability to observe this, so larger t values 1.15, and all t values that are actually, wait, is it larger? Is it, no, smaller. It's supposed to be smaller. I confuse this. This is smaller, this is larger. Okay. Okay, and observe that we know that it's supposed to be in the limit, the distribution is supposed to be normal and obviously symmetric, but we are not quite getting it empirically, but that's okay. So I'm, because of whatever numerical errors, imprecision, we are getting that the critical values on the negative and positive side are not the same. Otherwise, they will be usually the same. I mean, not usually, but in theory, they are the same. Now,
so that these t values are different just because in the data our tails are slightly different.
So these t values are different because of numerical errors, I guess. Well, because I need to make maybe b larger. Also, I have this imprecision because I'm dealing with
Okay.
the counts. So basically, supposedly, I mean, not supposedly, but for sure, if you increase b like 100 times, then you get more precision. And the rule of thumb is that for each digit of precision, you need to increase the sample size 100 times. It's a rule of thumb for like usually numerical errors, that numerical errors, it doesn't have to be the case, but like the first thing to try if you want to see if you get an improvement in numerical precision, you increase your sample size not 10 times, but 100 times. And then that should give you a precision in one digit. And you see that it's up to this second digit. They differ only in the second digit. So if I take b 100 times more, then supposedly they will start differing only in this digit. Now, the value is the value is this. And then let me write the last thing here. If t value is less than 0.5, we reject H0. Otherwise, we cannot reject H0. Perfect. Let me see, let me do, okay, I did something. What did I do here? Print p values, prob value, what?
You don't have a comma after the I think, after the text.
I don't think
No?
I don't think we need the comma. Let's see what is saying. And non-int and number count. Okay, what I'm doing here. Maybe like this. Would it work? Yes, it works. Perfect. So you see p-value is super large. We reject the hypothesis. So t-value is not too far away from the center, and so p-value, the probability of event that basically the probability that the true parameter is so far away is almost zero. And so p-value is very large. The probability, we say, like the probability of this hypothesis zero is high. Now, I want one thing, last thing to do here. I want to visualize this, and then we move on. So I'm going to use this trick. I want to have different colors. You'll see in a second what's happening here. So the baseline histogram will be blue. This is given by this. But I want to put in red the higher or lower values. Of this, you will see in a second. Set base more. Let's see. Okay, so this is what I wanted to see. So I'm taking this distribution. That's my kind of theoretical / simulated distribution. Again, I want to emphasize it like one millionth time. Oh, sorry, I have so many chat messages. Okay, sorry. Okay, it's you're following, right? It's like there was a message 10 minutes ago. If yeah, speak up if you have some problems, because I'm not checking the chat instantaneously, but you can copy paste from this notebook. Okay, so this is I took this distribution and then I see where t-value falls on it, and then I put in red all values larger or smaller than that. So these are all events that are as rare as this one or even more rare. And for example, for my t-value here, minus 0.5, 5, it's here. All this red to the negative are rare, or even more rare, or all this red to the right are even more rare. And then p-value is the sum of all the rare events, just by from the first principles. And so p-value is all this, the sum of the red things. Like we can, let me bring it up and just show you, like run it a bit. Like here, we get t-value very large, p-value 0.71. Lots of red, so we cannot reject H0 about our model. I want to get when we reject H0, and we are going to get it soon. Okay, we're almost there. You see, we got T very, which one? Very negative, and we're almost on the verge of rejecting. The red part is small, and that means that t value was so negative that it's very rare, such event, and we can say that maybe if this event is so rare, then we should reject H0.
Sorry, and could you repeat what's the null hypothesis here?
The null hypothesis is that R0 is 0. I mean, sorry, that the coefficient is 0. So this is, I generated the model with this coefficient 0. That's what I do here. I take rho equal to 0. Let me even do this. Then I estimate the linear regression with the intercept. And I want to check that the coefficient is really 0. Does it make sense? No?
Yeah, it's clear. And for different sets, you have the different results of rejecting the hypothesis or not. Yes.
Yes. Yes.
So should we set a seed to fix the results for not changing them every time we repeat the code or not?
You mean for this, for my demonstration, not. But for if you are doing like a home assignment, which you will be doing, I will let you know if you need to set the seed, because this is all just demonstration. You don't have to set the seed because I want this randomness. I don't care for reproduction of randomness. Aha, here we got t value quite large here, and basically we reject. So this is one case where we generated the model with the true 0 coefficient. We test the null hypothesis that this coefficient is 0, and we reject it because the t value is too large. All right, so now where do I want to go with this? Now I want to make things, how much more time do I have for this?
10 minutes.
10 minutes, okay, perfect.
Oh, yes.
10 minutes?
Yes, yeah.
Okay, great. So where do I want to go with this? Now I want to move to the time series. So now let me, oops, no. Now consider the following process. And now I want you to repeat this and tell me what you observe. Now it's your turn, actually. Epsilon. Okay, and where for epsilon t same let's say 1, just to be, well, okay, let's do sigma squared for the generality, but it's really, we're interested only in 1. Okay, now estimate this coefficient rho and tell me what you observe. Like, I want to see a histogram like that for that estimated coefficient. Let me, because this can be a bit, okay, let me not do this one, but because you might be stuck with how to merge the cells. So let me show you how to generate the data, but then I want to see, so let's say we again, like b is equal to whatever, 1000, t is equal to 100. Say we generate epsilon t equal into random normal 0, 1. Now I want to have size t plus 1. Yt is equal to t zeros t plus 1. So it's a bit different from before. I have, instead of t plus 1, so time 0, we start with 0, and then we start unwinding it. Walking through for t range 1, t plus 1, yt equal. And now I want to have, say, rho not 0, but say 0.9 multiplied by ytt minus 1 plus epsilon tt. Now I want, what I want to do with that. Series, I want to stack them column by column, and this is the fastest way for me to do it. So I translate yt into series, then I shift it shift all the values 1 time forward and stack them together. I will show in a second what that means. So let's say if I do it like this, then basically you see these are my values of yt. It starts 0, minus 0.95, and so on. And here at column 0, I shifted it 1 period forward, so it would be none, then 0, then minus 9, minus 0.95, and so on. So let me drop. So this is, once again, I just dropped the very first one. So we start 0, then 0.36, minus 44, and so on. Now I'm going to run a regression of yt on yt minus 1. And I want to estimate this coefficient rho through the linear regression. So I can also write this yt plus 1. Okay. I'm using a different way of running a regression. This is for demonstration, but then later it will be useful. I will show you later why I want to use it. Exogenous, then various zero. So exogenous is the first column. Yeah, and endogenous is the second column, so 0, 1, and then I think I need to actually both of them. It doesn't really matter. Let me do it here as well. Okay. Well, 1 second. Is it what I want to do? No, let me not do this yet. I will do it later because they're complicating things. Let me do it the old way. Okay, somewhere it's missing. Okay. Okay, so I start with 0.9, and this is the coefficient I estimate. Okay, now what I want you to do, so I guess there are 2 minutes left, but we can continue. I mean, we will take a break, I guess 20 minutes. You can do it during the break or during the next session. I want to see the distribution of row heads the same way that I did it here. So plot me the distribution of row heads, and I want to hear from you what you observe.
So now we have a break, or we do this thing?
Yeah, as you wish, but I want you to no, I want you to, like, I don't know, after the session starts in 15 minutes, to tell me. I don't need to see it. I want to, because I know how it should look. I want you to, like, say right now is what, 10:50 in St. Petersburg. I want in like 10:35 for you to tell me what you see from the distribution. Okay?
Okay.
Not 10:35, sorry, 11:35. Or if someone of you wants to tell me earlier, that's also fine. So I will mute, but write in chat if you're ready to tell me.